We are going to review the control structures we have seen during the lectures. We're going to have a look at several examples on real system diagrams. First of all, we can say that control structures can be split into two different groups. First of all, those who use a single controllers for their task, and the other group is about those structures that use several controllers. Well, when we say single controller or several controllers, it doesn't mean that we're going to use a single device and here we're going to use several devices, because a single physical device can gather within several controllers. So real PID controllers, they can be used on different control structures. For example, you buy a simple device, and this device can be configured as a single controller, but it can be also configured as a Cascade, a ratio, feed-forward controller, and the like. Well, if we have a look at these single controllers structures, here we have the selective. Remember, we have several PV variables, so we have several process variables. So the PV is obtained after a selection, so the word comes from selection, criterion applied onto several PV measurements. Remember that this is done because we have several measurements on a process that is so huge, and we cannot have just a single measure. For example, if we have like an oven, or we are controlling the temperature in a big room and the like, we can put several transmitters. So we have several process variables, and we are expected to choose, for example, the mean value. We can choose the maximum value, the minimum value, and the like. The selective control structure is also used when you consider that one or several out of your measurements can fail. So if, for example, you consider that a single measurement can be, a transmitter at the end can fail once, only a single transmitter out of all of your transmitters. If you use, for example, 3 transmitters, you can assume that one out of these 3 transmitters can fail, and the system will keep on working. Why? Just because this transmitter that fails is the single one that gives you a wrong measurement, right? Because the other 2 offers you similar measurements. So it's easy to know which sensor is failing. We're going to see afterwards an example. Then you have the split range. Remember, you have a single manipulated variable that is the output of a controller, and this manipulated variable is splitted onto several actuators. So this manipulated variable is delivered on several actuators. This happens, remember, when, for example, you can just increase the level in a tank by mixing hot and cold water. You can control the pressure for example, in a chemical process, just by acting on the input valve and the output valve. So you can split the manipulated variable onto several actuators. Then when we talk about those control structures that use several controllers, remember, it doesn't imply several devices, but at least one device that is using several control laws, several control operations, right? So we have the Cascade. Remember that the Cascade is this structure that has nested feedback control structures in the loop. right? So the set point of the inner secondary controller is the manipulated variable of the outer, the primary controller. So you mainly control the primary variable, right? But this control is assisted by an inner control loop, an inner feedback control loop, and the manipulated variable of the output of the outer controller is the set point for the inner controller. We will see later some examples. On the other hand, we have the ratio. The ratio, remember, when you are expected to keep a relation between a ratio at the end between two variables, then you use this control structure because two or more process variables are related each other. So a factor is applied. This structure is so typical when you want to keep a ratio between several elements in a mixture, when you have a combustion process and the like. Then we have the override, that literally means to pass over something. So this control structure can be found when several controllers are in competition for the single actuator you have. So here we have the sentence. Several controllers are in competition for the only actuator. So you are expected to have a switching criterion. This control structure can be seen as so similar to the selective. Remember that here on the selective, we have a selection criterion on several process variables. Here we have a selection criterion, but this selection is done on manipulated variables, not on process variables. Remember, the difference is that the selective has a single controller, several PVs. You have to do some operation with them, right? To take the maximum value, the minimum, not the maximum, not nor the minimum, the mean value, or something like that, right? Here on the override, you have several controllers, but the outputs of these controllers, so the manipulated variables, are in competition for the only actuator you have. So this selection criterion is applied on these manipulated variables, not on the process variables. That makes the difference. Then finally, we have the feed-forward control structure. Remember, this is an open loop control structure. In opposition to all the others, here you have closed loop. You have feedback control structures, right? But this is feed-forward. So apart from the feedback controller, the feed-forward is the only open loop structure in the control discipline. Remember that the feed-forward controls, the controller action of this feed-forward control structure is applied on a variable that is not measured. Remember, this control structure is applied to compensate the effect of a disturbance, to reject a disturbance. You will see. Well, now we're going to see some examples on the analysis of several diagrams, right? And the questions will be always the same. First of all, to name the set points, the SP, the manipulated variables, and the process variables in the diagram. Then write down the controller action, if it's direct or reverse, for the regulators. And at the end, explain the control structure in the figure and explain what is it aimed for, right? Well, first of all, remember, direct or reverse action of a controller. Well, the reverse action of the controller means, remember, that the error will be calculated this way. This is our set point, right? Here we have the process variable, so the measurement, and this is the error, right? So the error goes in here, the set point in here, and the process variable. Well, the reverse controller action means that the error will be calculated as the difference between the set point that comes here in the comparison as a positive signal, right? And here you compare the set point with the process variable. So you have the error as the difference between the set point and the PV. This controller action is applied when you have a process. Remember, here we have the controller. This is the controller. And then the controller action, that is the manipulated variable, is applied on our process. This process is fed back here. So this is our process. Here we have our transfer function. And this reverse controller action is applied when you have a positive relationship between the manipulated variable and the process variable. So when the process to be controlled has a positive relationship between the input and its output. So that means that when you increase the manipulated variable, the process variable also increases, right? In those cases, you will use the reverse controller action. So that means that the error will be calculated like this, right? But then you have the other situation, the direct controller action. The direct controller action is the opposite. It's a negative set point and then positive. So signals come into this comparison this way. So the error is obtained as the difference between PV that comes positive and set point that comes here negative. This is applied when you have not this situation, when your process is this way, when there is a negative relationship between the input and the output of the process. So that means that when you increase the manipulated variable, the process variable decreases, and the other way around. When the manipulated variable decreases, the process variable increases, right? So when you have a negative relationship between the input and the output of a process, then you use the direct controller action. So that means that the error will be calculated as the difference of the process variable and the set point. So let's have a look at this temperature control in a heat exchanger. As you can see here, we have the heat exchanger. Here in comes the steam at a certain pressure. Can you see here? So we have an inflow. We have here the condensed steam, because this steam gives heat to, we had a heat exchanger in here. So here it enters the cold fluid at an initial temperature with some inflow, as you can see here. And here we have the hot fluid. Here is the cold, here the hot. So now we have a different temperature. This is the initial, this is the final temperature. And the aim of this process is, as it says, to control the temperature of this outflow in here, right? So that's why we have here a temperature transmitter, a temperature controller. As you can see here, we have an external set point. This is the set point for the temperature, right? And here we have the process variable. This signal in here, this signal, is the process variable for the temperature, right? Here we have also the process variable, but it's the measured process variable. So you can put a star in here to make the difference between the process variable. This is these are the degrees, right? So it's the real temperature, and this is the voltage that explains this temperature, right? So this voltage is compared with this set point. right? And then we have the error, the control error inside this temperature controller, right? This will be the manipulated variable for the temperature, right? And here's this signal. And as you can see here, this manipulated variable, because it's the output of the controller, comes as the set point of an inner controller. As you can see here, we have the main loop, the primary loop, and here we have like a secondary. Well, it's not like, it's a secondary loop, right? So the manipulated variable for the temperature, it's also the same as the set point for the flow controller structure, right? So when you have that the set point of an inner control structure, an inner feedback control loop, is the manipulated variable of the outer control loop, we have a cascade control structure, being the flow control, the inner loop, the secondary loop, and being the temperature, the outer or the primary control loop, right? As you can see here, we have the flow transmitter. Here we have the process variable for the flow. Here, the measured process variable in volts or in milliamperes, right? And this is the controller action. This is the manipulated variable. Here we have the manipulated variable for the flow controller, right? This is applied on this proportional valve, and well, the system reacts to an increase or an increasing flow for the incoming steam, right? Well, now we are expected to stay if these controllers are in direct controller action or in reverse controller action. So now let's gonna study what's the effect. First of all, if you increase the controller action in here, so if you open the valve, if you increase the inflow, the steam inflow, it's expected that the temperature will increase. So because an increase in here, we have a positive, an increase here in the an increase of the inflow implies an increase on the outer temperature in here. We can say that this controller can be configured in reverse action, right? So here we have a reverse controller action. And the same goes for this flow controller, because when you increase the controller action, when you open the valve, the inflow increases. So we have a positive relationship. So this is also a controller configured as a reverse controller action. Then on the other hand, we have a flow control in a mixing tank. Well, as you can see here, we have here an inflow B, an inflow A, and as you can see, we measure both inflows in here. We have a flow transmitter and a flow transmitter in here. As you can see, this is the process variable. Well, if you want, you can say that this is the process variable and this is the measured process variable, right? Well, at the end, there is no difference, just because here the process variable is in volume per second, for example, right? And here we have a voltage or a current, right? We have volts or amperes. The same goes for this flow transmitter, because here we have the process variable, the physical process variable, remember, in a volume per second, right? And here we have the voltage or the intensity, so an electrical variable that is the measured process variable, the process variable that is measured by this transmitter, right? Well, as you can see here, we apply a block with an R on it. This R gives us some clues, right? Because R comes from ratio. But as you can see here, we multiply the process variable by this factor, and this becomes the set point of this flow controller. So just because we have a relationship between this process variable and we want to keep this relationship, this R value between both variables, because the set point is R times the process variable of this B inflow, then we can state that this is a ratio control structure, being the set point R times the other process variable. So when this controller makes the error equal to 0, we can say that there is a relationship between this variable and this variable. Let's gonna have a look at level control in a tank. Here we can see that we have a tank, then we have a pump here at the out, well, in order to make the outflow, right, of this tank. Well, the aim of this pump is to make this outflow so linear, right? Because if you don't put a pump, if you just put a valve, the outflow will depend on the square root of the level in this tank, right? From the water level or the liquid level in this tank. So the pump is put here just in order to make the process so linear. Well, as you can see, we have a level transmitter, so we can say that this is the process variable. If you want to be more formal, the process variable itself is this, because this is the physical variable in centimeters or whatever you want, right? And here we have the equivalent voltage or intensity, right? Because it's the out of the output of the level transmitter. So this is the process variable. This is the measured process variable. But we can say that there is no difference, because at the end, the important signal is this, because this signal is the electrical signal that will be compared to the set point, right? Well, here we have a level controller. This is the set point. And this level controller, as you can see, the output of this level controller is applied as the input of a flow controller. So we can say that here we have again a cascade control structure. We can say that this is a repetition of the first example that we have seen, because here you can see that we have a flow transmitter, a flow controller, so we can say that there is also a cascade control structure, and that's right. But as you can see, that this is the primary loop and this is the secondary or auxiliary loop, we can see that here we add a different signal, right, to this controller action. Just because this is a manipulated variable, because it's the output of a controller, this must be also a manipulated variable, right? So that's why we can say that this is also a controller. But as you can see, this controller action is applied at the end on a valve that doesn't modify the variable that this controller uses as a measurement, right? So we can say that this controller is controlling a variable that is not measuring, right? So this is clearly an open loop controller. So this is clearly a feed forward controller. And the aim of this controller is that it measures, or it is given the measure of the inflow. This could be a disturbance, a change in this inflow variable, right? And it applies a controller action just before the effect of this disturbance is noticed by the level transmitter. So that's why it's a feed forward. It applies a controller action in advance, just before the disturbance affects the variable we are interested in, right? And obviously, this feed forward must not be configured in a direct or reverse action because it doesn't calculate the error signal, right? Because as you can see, the input is the disturbance and the output is the controller action that is added to the primary loop controller action. So here we have two controllers. We have a feed forward and a cascade control structure, as you can see here in the figure. So now let's gonna have a look at why this is a reverse controller action and this is configured with a direct controller action. This controller is configured with a reverse controller action just because when you increase the controller action, so when you open the valve, the outflow will increase, right? So there is a positive relationship. When you open the valve, the effect, that is the flow, will also increase. So we have a positive relationship in the process we are controlling. We are controlling the flow process in here. So that's why this is configured with a reverse controller action. But what about the level controller? When you increase the controller action, so when you open the valve, the level in the tank is going down, right? So that's why we have a negative relationship between both variables. When you increase the input, the output, the effect, that is the level in the tank, decreases. So that's why we use a direct controller action, because we have a negative relationship between the input of the process, that is the opening of the valve, and the effect, that is the level, because we are now considering the level controller. Let's gonna have a look now at a mixed level and flow control in a tank. As you can see, the situation is quite similar to the previous one. We have a pump here for the outflow of this tank. We have here the inflow, and we have a level control loop, as you can see here, but we have also a flow control loop, right? But the first thing we must be noticed is that here we have a selector, and this selector is configured as a low selector. That's why lower than this symbol is the same as the low selection criterion, right? So we have two inputs and we must select all the time. Well, at the end, the aim of this block is to select all the time the smaller signal that incomes to the block. As you can see here, we have two controller actions because this is the output of the level controller and this is the output of the flow controller, right? So because we have a selection between two controller actions, we have an overwrite control structure, right? And what is this overwrite controller action used for? Well, this overwrite control structure and all override control structures are used to protect the actuators, because typically is selecting this flow controller action. Why? Just because here we suppose that we need some inflow here, because here we have another process. I don't know what process do we have? But here we have another process, right? So we need an inflow, a constant inflow of this liquid, right? But what it happens if this level is going down, 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 and down? If this tank runs out of liquid, right, we will have a real problem. Just because here there will be no liquid and this pump will be damaged, right? So in this case, this selector will select the controller action for the level control loop, just because if this level is going down, down, and down, this controller will say, just stop the pump. So because this controller action will be stop the pump in order to protect this pump, which variable, which manipulated variable will be the smaller? This one, for sure, because this variable will say, just stop the pump in order to protect, because you are running out of liquid, right? Because, I don't know, here the liquid is not coming, is not incoming, right? So you are running out of liquid. So that's why typically this override control structure is working with the flow control loop. But when you have an issue because you're running out of liquid in here, this level controller takes control of the situation in order to protect this pump not to be damaged. Well, this level controller is configured on a direct controller action, just because if you increase the power applied to this pump, the level decreases, right? So that's, we have a negative relationship between the input of the process, that is to apply an increasing signal here in the pump, right? And the output, that is the measurement, the level measurement in here, decreases. So that's why we use direct controller action. And this is configured with a reverse controller action, because if you increase the speed of the pump right here, you are increasing the flow here at the out of the pump. So you have a positive relationship. That's why we use a reverse controller action. Let's gonna have a look now at the level and flow control in a tank. This is absolutely the same situation that the previous example, but now here we have added a valve, right? But as you can see, this selector selects out one out of these two manipulated variables, because these are the outputs of these two controllers. Remember that this is an override control structure, and this selector, we can say that this will be configured as a low selector, because when the level controller says stop the pump, well, in this case, it's not stop the pump, it's just close the valve, right? In order to not to run out of liquid in here. Because if you run out of liquid in here, then this pump will be damaged. Remember that we have a process that typically needs an inflow. So that's why typically the flow control loop is working. But when there is a critical situation, the level controller takes control of this situation in order to protect the pump. So we can say that we have an override, and with because we have the same situation that the previous example, the level controller is configured with a direct controller action, while on the other hand, we have this flow controller as a reverse controller action. Let's have a look at the house temperature control. Here, as you can see, we have inner measurements of the temperature in the house, right? Here we have several measurements of the temperature here in the burner, right? As you can see here, right? And then we have the fuel admission in here, the air admission. So we can figure out that if we have a combustion process in here, we will have a ratio control structure. As you can see here, we have a ratio control structure, right? Here, you can see the R. So that's why we are measuring, as you can see, the flow in here. We are measuring the flow in here, right? And this measure is multiplied by this factor, this R, and gives the set point for this flow controller. So we keep a relationship between the fuel and the air in order to get an optimal combustion here in the burner, right? Well, as you can see here, we have a set point for this temperature controller. So this is the set point in here. Here we have the set point, and this must be the process variable. But as you can see here, the process variable is obtained thanks to a selection criterion applied on several transmitters. So here we have a selective control structure because this selection is applied not on manipulated variables, because in this case we would have an override control structure. We have, in this case, a selection control structure, just because we are selecting among these transmitter values, right? So that's why we take here the maximum value. I think that it's in order to measure, well, to take the highest measure in order to protect this temperature, well, to protect the burner at the end, right? This is the heating system at the end, right? And as you can see here, the temperature controller, the output of this temperature controller, so the manipulated variable, goes to another selector, right? Well, if the output of a controller is going to a new selector, we can say that, or we can foresee that we have here an override control loop. So this is a selection, but this will be an override because now we are comparing, not comparing. At the end, we are doing the selection, applying the selection on several controller actions, right? Manipulated variables, because this is also a manipulated variable. Here we have the temperature controller. Remember that here we have an I in the middle. This I is for the indicator, right? So that means that this controller, well, I think that there is some kind of a panel mounted device, right? Or wall mounted device. And here we have something like a screen, a small display, right? In order to show the user the actual or the instant values for the temperature within the house, right? Here we have also a selection control strategy, just because we select, well, at the end, we apply the mean value among all these temperature measurements, right? So because we are selecting on several measurements, we can say that we have a selection control structure. And this process variable comes to the controller. Here we have the set point, right, in here. So this is the process variable, this is the manipulated variable, and we select the smallest value, right? This value, this is a controller action, is applied as the input for this flow controller. So we can say that we have a cascade control structure in here. So this control system is so complex because here we have a selection. Here we have another selection. Here we have an override. Then we have a cascade just because the output of this selector is the input, so the set point, for another controller. So this is a secondary loop. The main loop is the temperature, the house temperature or the heating system temperature, right? And then the secondary loop is this fuel flow control, right? But on the other hand, and finally, we have the ratio control structure. So we have 1, 2, 3, 4 the cascade, and 5 the ratio. We can summarize that we have 5 control structures in here. Well, the controllers must be configured this way. This as a reverse, because if you increase the flow of the fuel, right, the heating system temperature will increase, and at the end, obviously, the hot water will be hotter than the original, right? So the temperature in this, within the house will increase. So we have a positive relationship. Then we use a reverse controller action that can be applied to the temperature control within the heating system, and both controllers, both flow controllers here, are configured in a reverse controller action, just because if they open the valve, so if they increase the controller action, the flow will also increase. The fuel flow and also the air flow. Well, let's now gonna have a look at this chemical reactor control, right? Well, as you can see here, we have several temperature transmitters that measure the temperature in this exothermic reaction, right? It's measuring this inner temperature in the tank, right? As you can see, the output of these 3 transmitters come to a selector. This means that the output of this selector will be not the maximum nor the minimum value of these transmitters. And this is used when you don't trust on the temperature measurement. You consider that one transmitter can fail at a time. So then you use 3 transmitters because 2 transmitters are giving you similar measurements, right? Not exactly the same, but so close measurements, right? And 1 transmitter is giving you, I don't know, it will depend on the fail, right? 0 or 100%, right? So because you don't know how it will fail, but you have enough, you trust enough on the measurements, just because you only consider that one out of them can fail at a time, right? But you don't know how it will fail. You don't know if the measurement will be the lowest value in the scale or the highest value in the scale. That's why you use not the maximum nor the minimum value. So if you have one that is giving you the minimum value, the other one a value, and another one that it's a value so close or similar than that, if you don't take not the maximum and not the minimum, you for sure will take a value that is a correct value, right? If on the other hand you don't have a fail about a measurement, a lowest value in the scale measurements, right? You have the maximum 100%, right? This is the fail, 100%, right? If you don't take the maximum nor the minimum value, for sure you will take a value in the middle. So the value in the middle will be a correct value, right? So we can say here that we have a selection control structure, right? And this selection control structure is applied on the temperature control here by just opening or closing this cold water in the here in the jacket that is helping us to control the temperature here within the tank where the chemical reaction is produced, right? Well, on the other hand, here at the bottom right of the figure, we have a level control, as you can see here, and the output of this level controller, so the manipulated variable, is the input, so the set point of this flow controller. So we have an inner control loop, we have an outer control loop, so we have the main, we have the secondary, the main control loop, the primary loop, and the secondary or auxiliary control loop. So we have a cascade, clearly a cascade control structure. Remember that this element in here is a transducer that only changes the current that comes out from the controller into pressure in order to open or close this proportional valve, right? So remember, selection in here, and here a cascade. Here we have also a selection control structure. I will not repeat myself because it's the same, but now not for a temperature transmitter, now is for an analysis transmitter. So we are like analyzing here the product that is the result of this chemical reaction, right? And we don't take the maximum value nor the minimum value. So we also can figure out in here that we don't trust that all the measurements will be fine, will be right. So we assume that one out of these transmitters can fail. So that's why we use 3, because 2 of them will give us the right value, right? For example, if you consider that 2 transmitters can fail at a time, you should use 5 transmitters, because 2 will fail, but 3 will give you the right measurement, right? If you take one in the middle, for sure you will take a right measure. Well, here we have the analysis controller, and the output of this controller, as you can see, is the input, is the set point of a flow controller. So again, we have a cascade control structure. So now we have 4 control structures, 2 selection and 2 cascades. But as you can see here, we have an R here multiplying the measurement of this flow transmitter. Can you see here? So that is a ratio control structure in here, because we have also a flow controller in here, right? Here we have the measurement, the flow transmitter. Here we have a flow controller, again, another flow controller, but we, as you can see here, we want to keep a relation, a ratio between these 2 variables, right? This variable in here and this variable in here. So that's why we use this R. So we have selection, selection, 2 cascades, and a ratio control structure. Now, how can we, or how should we configure all these controllers? Well, first of all, this in here will be configured as a direct controller action. Why? Because this is a cooling system, not a heating system. So when you open the valve, when you increase the inflow here of the cold water in the jacket, you decrease the temperature. So because you have a negative relationship between the input and the output of the process, you must configure this controller as with a direct controller action, right? Well, here this level controller, remember, if you open the valve, if you increase the controller action, if you increase the input of this system, the manipulated variable that you have, the output of the system, that is the process variable, the level variable, will decrease. So you have a negative relationship, direct controller action. But be careful, because here we have a flow controller. If you open the valve, if you increase the controller action, you increase the process variable, right? So that's why we have a positive relationship between the input and the output of the system. So this must be configured as a reverse controller action. Well, the same goes for this flow controller in here. And for this flow controller, if you open the valve, the flow increases, right? But here, we don't have enough information because we don't have information about if we increase this input in here, we don't know if this analysis results will increase or decrease, right? So that's why we don't have, because we don't have enough information, I cannot say here if this is a controller that must be configured with a reverse or direct controller action. So the solution must be to write down that this controller action at this moment, we cannot say that we must configure with the direct or reverse controller actions. So we should ask the chemical engineers or the chemical staff, right, in order to tell us if we increase this variable, what it will happen with this analysis transmitter values, right? If the relationship is positive, then we will use the reverse controller action. If the relationship is negative, we will use the direct controller action. So, well, now let's go for the design, right? For the design exercises. So here we will be asked, for example, to state the number of actuators and the number of sensors to be acquired in order to develop an optimum control of the system according to the specifications of the exam statement, right? Then place all the components, to place the components on the diagram, right, according to the ANSI ISA norm. And finally, to draw the control structures for this system. Well, first of all, we are asked to design, according to this norm, an automatic steering and cruise control for a car. You can use a gyroscope sensor, so it's a position transmitter, right? That is why we use the ZT. It's a position transmitter, gyroscope, that provides the car direction. It can be also used an absolute encoder, also a position transmitter, that provides the car steer, the wheel directions, right? And then the car speed meter, that is this, right? We have this, well, sorry, here we have, this is a nasty, it's a mistake, right? I'm sorry, this is not an AT, it's an ST, it's a speed transmitter because we are talking about car speed meter. The actuators are an electric motor that steers the wheels and the fuel admission valve. Well, my proposal is the following. As you can see here, I have a position transmitter, and this position transmitter is the absolute encoder that measures the steering system, right? The car steer, the wheel direction in here. Then this is the process variable, as you can see here. And here we have the position controller, that is the wheel direction controller, right? As you can see here, this manipulated variable, this is the manipulated variable, is applied on the DC motor in here. And this DC motor changes the wheel direction. Well, here we will find that the set point of this controller comes from the output of an outer controller, because this controller in here, this ZC, is the orientation, the car direction controller. So we measure in here, this is the gyroscope sensor. Here we have the gyro. This gyro informs about the direction that takes the car. And this is the PV. Well, this is the PV. This is the measured PV, remember? Here we have the controller, and here we have the external set point for this controller. As you can see, the output, as I said before, the output of the autocontroller is at the same time the input for the inner controller. So the primary loop in here, so we have a cascade loop, obviously. The primary loop is the car direction, and the secondary or auxiliary loop is that one that controls the steer, the wheel direction, the car steer, right? As you can see here, we have something added to the primary controller action, but I will talk about this just later on. I will take this signal later. Well, as you can see here, we have another controller, another controller strategy. This is a feedback controller strategy. As you can see, we measure the speed of the car. This is the speed transmitter, that ST. Remember that this is not AT, is ST. And here we have the speed controller. This is the set point. And as you can see, the controller action is applied to the fuel admission valve. Well, I told you before that I'm going to talk about this addition in here for the cascade loop. And it's very important because the car direction will change not only depending on this controller action, right? On this direction or position controller action, but also will depend on the speed of the car, right? For a specific steer, for a specific wheel direction, right? Depending on the speed, the arc that will describe the car will be so different depending on the linear speed, right? So that's why the car direction that should be the tangent to these arcs, to these curves, well, this speed will affect the car direction, right? So that's why here, depending on the measurement, I propose to apply a feed-forward control strategy in order to control in advance the car direction, to apply an additional manipulated variable for that car direction. So that's why it is added to the primary loop, that is the car direction control. This exercise was stated in the 2019 exam. The figure shows the diagram of a boiler. Can you see here a boiler drum with different control structures? The level of the boiling liquid is measured and used to adjust the feed water flow rate. This control system tends to be quite sensitive to rapid changes in the disturbance variable, steam flow rate. This is the disturbing variable, right? As a result of a small liquid capacity of the boiler drum, you are asked to name the set points, manipulated variables, and process variables in the diagram, and then write down the controller actions, direct or reverse, for the regulator LC, for this LC, right? Well, because this is a level controller, because here we have feed water. The more water it enters to the boiler drum, the higher the level. So we have a positive relationship. This controller must be configured in a reverse controller action. So this question is so fast to answer. Well, then the set point, manipulated variable, and process variable is very easy. As you can see here, we have the process variable, the measured process variable. So you can say that here we have PV, here PV star, in order to make the difference. But at the end, remember, this is only a translation in an electrical form of this physical variable. These centimeters will be translated into volts or amperes. Well, this is the controller action, right, in here. And finally, this controller action is applied to the admission valve, right? Well, we can see here that we have a flow transmitter. Let's see later what's the task connected with this flow transmitter. But as you can see here, we have some signal added to this manipulated variable. Here we have a manipulated variable for the level controller. So it's very easy to see that this must be a controller action. So this symbol in here is a controller. The second question asks about this symbol. What is the element symbolized in here? Well, at the end is a feed forward controller, because we are measuring some variable, but we are not applying any direct controller action to this variable. So we are measuring this flow, but here we don't have a valve in order to apply the controller action. So because we don't have that, we can assume that this is an open loop control strategy. And this is a feed forward because it measures the disturbance and then it applies the controller action, the compensation action, to the primary loop, the main loop in this diagram, that is the level control loop. Explain the control structure in the figure and explain what is it aimed for. Well, at the end, this is in order to compensate this feed forward in here, in order to compensate the disturbance on this outflow, this steam outflow, right? That will obviously affect the level in this boiler drum. Remember that the capacity is so small in this boiler drum. So for sure, it will affect the level in this tank. So we add this, well, the designer adds this controller action in advance to the feedback, the typical feedback control loop. Then consider a sudden change of the flow change in the feed water. So we are talking about, we're discussing now about the feed water. Explain thoroughly the actions that take place in the system as a consequence of this event. Well, if something changes in here, obviously the level will be affected. So that's why, for example, we can foresee that this flow transmitter can be used by just adding a flow controller, right? Here we put a flow controller, and then this flow controller will apply the controller action in here, and this signal in here will be the set point for this flow controller. So this way, we have a cascade control loop in here with the feed forward action added to the primary loop, because the primary loop is the level control loop, because this is the main objective of this control strategy, right? And this is the auxiliary or secondary loop. As we have stated during the lectures, the secondary loop tries to linearize or reject the disturbances that may happen in the system just before they affect to the outer, to the main, to the primary loop. So now with this cascade control strategy, if any changes, any sudden change happens in this feed water, it will be, this disturbance will be rejected thanks to the flow controller loop. Well, this, you may think that this will imply, this implies the acquisition, the buying of a new device. But as I told you at the beginning of this video, multiple controllers do not imply multiple devices, right? So the same controller, the same digital device can perform all these control strategies, right? So it's not expensive to add this controller. If you have the sensor, if you have the transmitter, it's quite easy to add this signal to the device, to the controller, and to configure the controller in a cascade form. Well, consider section E, consider that the water level in the tank is so critical, and consider also the disturbances that can happen in the feed water. Design 2 additional controller structures in order to improve the performance of the system on disturbance rejection and protection of the boiler. Start with FT. You can add as many sensors and controllers as needed. Well, here, the disturbance will be rejected by my proposal, my Cascade proposal, right? But because here the keywords are that the water level in the tank is so critical. So let's think about this level transmitter. If it fails, this control will, well, at the end, the system will be damaged because this control will not work properly, right? So my proposal is to add, for example, 2 additional level transmitters, and then we have the assumption that one may fail at a single time, at a specific time. So here I will put a selector, and this selector, the selection criterion, will be not the lowest nor the highest, right? In order to take any value in the middle. So if any of these level transmitters fails at a specific time and only one transmitter fails, I can take the value in the middle that for sure is right. Write down the controller action, direct or reverse, for the added regulators. Well, this controller in here, this flow controller, will be configured in reverse action, just because if you increase the controller action, if you open the valve, right, the feed water will increase. So we have a positive relationship between the input and the output variables of this small process. So a reverse controller action will be used for this flow controller. Well, here you have more clearly my design, right? As you can see here, the selector, not the lowest nor the highest, the 2 additional level transmitters. This obviously will be configured in a reverse action, I told you before, and the same goes for this. And as you can see here, we have the cascade, we have the selection controller strategy, and additionally, we have the feed-forward controller. Well, the figure below shows the diagram of a control tank system. You are asked to name the set points, the manipulated variables, process variables in the diagram. Write down the controller action, direct or reverse, for all the regulators, FC, LC, and ZC, and enumerate the controller structures that can be shown in the figure and explain what they are aimed for. Well, as you can see here, we have a main level control, right? This is the primary loop, as you can see. And the output of this controller becomes the input of an inner loop, an inner flow loop. And the output of this inner flow loop is the input of an inner position, because that, remember, goes for position loop, the position of this valve, right? If it's more or less, if it's open at a specific point, right? That's the position of the valve. That means the opening rate, right? So as you can see here, we have a triple cascade loop. The outer one, the main, the primary, is the level control loop. Then we have the flow. This is a secondary, an additional secondary loop. The inner loop, the innerst loop, is this position control, right? So we have a triple cascade in here. As you can see, we add another controller action. I know that this is a controller action because this is a controller action. This is a manipulated variable. So this, obviously, not only for the C letter, this is a controller. right? And it's a feed-forward controller because its controller action is applied on a section of the system that has nothing to do with this first section of the system. So here we have a classical feedback loop, and this is a feed-forward controller. So, well, we have a triple cascade in here, we have a feed-forward controller, and here we have a classical feedback control loop. The controller's actions is reverse. In here, we are controlling the flow, right? It appears so often, this control strategy. This is also reverse. If you increase here the pressure in this valve, the valve is opening in a highest grade, right? Then here, the same situation than here. If you open the valve, the flow will increase. And this will be configured as a difference to the others, right? In a direct controller action, just because if you open the valve, the level in this tank will decrease. So a negative relationship between variables, direct controller action. The figure below shows the diagram of a controlled exothermic reaction process. You are asked to the following. It's always the same: to name the variables and write down the controller actions, right? Design some additional control structures in order to improve the performance of the control system. Draw all the elements in the figure below, obviously. Use all the transmitters that are present in the diagram. As you can see, you have some idle transmitter in here, you have some idle transmitter in here, and the same goes for this. Well, and finally explain the aim of the proposed improvements. Well, here we have the incoming product, right, that is measured, and we are doing nothing with this. We are measuring these flows, right? And as you can see, we are measuring the temperature within the tank, and then we are controlling this temperature, right? Fine. We are also measuring this level in here. We are controlling the level of the liquid here, of the product we have here in this reactor, right? So we are controlling this level. So both the temperature and the level are controlled. Fine. Well, the additional control structures could be, for example, here, that we are applying the temperature. As you can see here, the temperature controller action. We can add, for example, here, a flow controller. Here, we put flow controller in order to reject any disturbance that may happen in here. And be careful. I want to make the difference between this flow in here and this flow in here. Here we have the jacket, the cooling jacket. Can you see here? The cooler enters in here and then it goes out through this way. Here in comes the product, right? Here the reaction is produced and then the product gets outflows from the tank through this way, right? So here we have the cooler and here we have the outgoing product, right? So that it's very important to make the difference, right? So, well, an inner or auxiliary control strategy is added in here. So my proposal is to build here a cascade control loop. Remember that it doesn't imply to buy a new device. The same temperature controller can do the flow controller action, right? So the device will be configured in a cascade way. On the other hand, we have here the level controller, so we can do the same. Here, we can add a flow controller, and this flow controller will receive the set point through this way by means of the controller action, right? And obviously the measurement will the flow rate measurement will come from this transmitter, right? Well, finally, So here we have also a cascade control loop. So 2 cascades is my proposal. But if any disturbance appears here in the incoming product, we can use this transmitter in here. We can add a feed-forward controller, and here, as you can see, this feed-forward controller action can be added to the primary loop, the primary level control loop, right in here. Remember the cascade? Here we have the inner loop. So the feed-forward controller action will be added in here, just because if the incoming of the product changes, we can modify the outgoing flow rate of the resulting product, right? Well, the remaining thing to do is to configure the controllers with a direct or reverse action. Well, here it's this flow controller is a reverse action. If you open the valve, the flow will increase. The same goes to this flow controller, reverse action, because we have a positive relationship. Opening of the valve implies the increasing of the flow rate, right? Well, here this level controller is configured in a direct action because the valve is for emptying the tank. The valve is at the output. Remember, if you open the valve, if you increase the controller action, the level in the tank will decrease. So that's why here a direct controller action, right? Well, this temperature controller in here, right, is configured with a direct action because we have a negative relationship between variables. And the negative relationship is because if you increase the inflow here in the cooler, well, the cooler will not take so much temperature. So the gradient between the inner temperature and the jacket temperature will be higher, so the temperature in the tank will decrease. So that's why we have a negative relationship, so a direct controller action must be configured.